Hi guys, the first problems I wanted to look at out of Chapter 2, Section 1, these difference quotient problems really caught my eye in this section. These 44 through 50 and the even problems in the homework. I did several of the odd problems in the homework assignment where I showed the answers in my homework solutions. I actually want to look at every single one of these even problems, and this is something worth driving home the point of how to do these problems, because this is actually the developing concept behind what is a derivative in Calculus 1. So when I look at these with you here, to start off, the first problem I wanted to look at asks me to apply the difference quotient to f of x equals 3x squared plus 2. So the difference quotient formula says that all I need to do is evaluate f at a plus h, subtract from that f evaluated at a, and divide this by h. All this really is the change in y over the change in x. F of a plus h is going to be taking the place of y2. F of a is taking the place of y1. The change in those two x values, well, they're only h units apart, a plus h minus a. But now the point of the difference quotient is to apply this to this function. So I can say, well, all right, if I apply f of a plus h to this function, it's going to become 3 times the group a plus h squared plus 2. All of this is f of a plus h. From that, I subtract f of a. So I'll say, well, the group f of a, it's just what you see up there, except instead of 3x squared, it becomes 3a squared plus 2. So I have my f of a plus h minus f of a over h. Now I need to try to simplify that down. So I'll just do the algebraic maneuver of squaring this out. We know a plus h squared, that means a plus h times a plus h. That would be a squared plus 2ah plus h squared. Well, I need to distribute a 3 through that group. I can say, well, when I do that, I'll have 3 times a squared plus 6ah plus 3 times h squared. Now that's distributing 3 through the first group. I still have a plus 2 in there. All of that becomes my f of a plus h. I'm subtracting from all of that f of a. So minus 3a squared plus 2. I have my f of a plus h minus f of a over h. Now, whenever we try to simplify this, my numerator, please notice, any term that can be canceled out must be canceled out. The 3a squared minus 3a squared cancels. I'll have 2 minus 2 cancels. Now, every single term that's remaining in the numerator will always have a factor of h left in it. So I'm so confident I can factor out an h every single time. Before I even look at it, I'll say factor an h out of whatever's left in your numerator. And you can see, yeah, we can do that. The only two terms that didn't cancel are the 6ah and a 3h squared. If I factor out an h, I'll be left with 6a plus 3h. And then I can say, well, that's going to be divided by h. Here, the h's cancel. And I can say my final answer here is just 6a plus 3h. Now, we'll be talking about what we can do with this in class later on and in further sections, specifically when we start talking in section 2.4 about the average rate of change of a function. This really leads nicely into that. So right now I'm not going to really put many applications with it. I'll just do the algebra involved in the problems, and we'll talk about what we can do with this later. A second problem here, this is actually 46 in the section. I'll say f of x is equal to, this time we have a fractional problem, 1 over x plus 1. And again, the goal of this is to apply the difference quotient. The difference quotient asks us to evaluate f of a plus h minus f of a over h. Okay, so if I apply that to this function, f of a plus h. All that's saying is wherever you see an x in your function, replace it with an a plus h. So 1 over x plus 1 becomes 1 over a plus h plus 1. And then I'll say minus f of a, well, that's just going to be minus 1 over a plus 1. All of this over the denominator of h. So I have my f of a plus h minus f of a over h in here. Now you should automatically say, oh, you have a compound fraction. Fractions within a fraction. There is no question what the next step needs to be. You need to get rid of the fractions in the fraction. So I'll multiply by a plus h plus 1. And I'll multiply by the factor of a plus 1. We have to multiply by those factors in both the numerator and denominator. Then I can say, okay, at this point, our simplified numerator, when I distribute this through, that first term, 1 over a plus h plus 1, will cancel with this. The first term, I'll have an a plus 1 left over. I really don't need a group around it, but I'll put it anyway. And then I have minus. Now the reason I put the group around the first one is to show that I absolutely must put a group around the second one. Why? Well, this a plus 1 is going to cancel out this a plus 1, but I'll still have a negative 1, or a minus, times the group a plus h plus 1. You can't just subtract the first term, you're subtracting the entire group. Now my denominator, it already had the factor of h. We'll have an a plus h plus 1 times a plus 1. Now, every single time in these problems, a lot of times students are confused about what they need to do and when are they done. You're done when you simplify the numerator and you can factor out an h and cancel it with the h in the denominator. If you haven't canceled that h in the denominator, you're not done with the problem. So right now I can't cancel out the h, but now look. If I cancel, I can say a minus a goes away. 1 minus 1 also cancels. So the only thing I have remaining in that numerator is a negative h. So negative h over the factor, h times a plus h plus 1 times a plus 1. Now I can cancel out the factor of h in common in the numerator and denominator and say when that cancels in the numerator, I have a negative 1 remaining, all divided by a plus h plus 1 times a plus 1. Final difference quotient problem. If I go to the next one, the next even problem here under this difference quotient section gives us f of x is equal to, and we have 2x over x minus 1. Well, 2x over x minus 1, trying to use the difference quotient on that fraction. So I'll say, okay, well, f of a plus h minus f of a, all divided by h. Apply that formula to this problem and simplify and cancel out h in the denominator when we're done. Okay, this one's going to be a little bit more complicated, but that's fun. Each fraction, I'll have 2 times x. Well, 2 times x is going to be 2 times the group a plus h. My denominator, I'll have the group a plus h minus 1. Since a plus h, or since x down in the denominator is not being multiplied by anything, I don't need to put a parenthesis around the group a plus h replacing it. I'll say my denominator is just a plus h minus 1. Now when I say minus f of a, I write the exact same fraction I have here, but everywhere you see an x, you replace it with an a. 2a over a minus 1. All over h. In order to simplify this expression, I'll need to multiply in the numerator by a plus h minus 1 and by a minus 1. Of course, we have to multiply by those same two terms in the denominator. We're multiplying by an understood 1 there. And now, when I distribute this product into the numerator, when it goes into the first term, this a plus h minus 1 will cancel out this a plus h minus 1, but I'll be left with 2 times a plus h times the group a minus 1. We'll have to multiply that out in the next step. My other term is going to be minus 2a. The a minus 1 would cancel, but I'll have minus 2a times the group a plus h minus 1. And all of this is over the combined denominator, all multiplied across, h times a plus h minus 1 times a minus 1. The goal of the simplification process of this difference quotient is I've got to get a factor of h in that numerator to cancel with the factor of h in the denominator. Once I can do that, I'll have the final difference quotient solution. In the numerator, up here just real quick, I'm going to go ahead and FOIL out the a plus h times a minus 1. It would give us, a times a is a to the second, then we'd have minus a, then we'd have plus AH, and then I would have minus H. Now the reason I went ahead and did that there is because we need to multiply all of that by 2. So down here in the next step I'll say, okay, I have 2a squared minus 2a plus 2ah and minus 2h. When I distribute the minus 2a times every term in this group here, I'll have minus 2a squared, and I'll have minus 2ah, and I'll have plus 2a. Now this brings up an important point I forgot to mention earlier. The terms of f of a plus h and f of a, they will always cancel. They never combine. So if you find yourself, after you've simplified out the terms of f of a plus h, which remember, all these first 4 terms came from f of a plus h, these last 3 terms came from f of a. The terms always cancel. You'll never be saying, hey, 2a squared plus 2a squared is 4a squared. They will never combine. They will always cancel out. And so if you're combining, you know you've done the wrong algebra. So let's see if I've done the correct algebra. 2a squared minus 2a squared, hey, they cancel. Excellent. Positive 2ah minus 2ah, they cancel. Wonderful. I have negative 2a, positive 2a, precisely what it's supposed to be. They will always cancel, never combine. So then you say, after you've canceled out the terms that are supposed to cancel, the only thing you're left with in the numerator is that measly little minus 2h. So this ends up being similar to the last problem. I'll say, well, my numerator's negative 2h. My denominator has the factors of h times a plus h minus 1 and a minus 1. I can cancel out the h since it's a common factor in the numerator and denominator, or as I like to say, I eliminate h. Now my numerator is just negative 2. My denominator is going to be a plus h minus 1 times a minus 1. Absolutely cool final answer there. Now you're thinking, wow, they can't get much better than that. Well, anytime we have polynomials to higher powers, it gets a little bit more complicated. In number 50, that I'll say is my problem number 4, I wanted to work the 5 most important problems in this section. It gives us f of x is equal to x cubed. So f of x is equal to x cubed. What I'm going to need you to remember here is that if I have a plus b to the 3rd power, that is equal to a to the 3rd plus 3a squared b plus 3ab squared plus b cubed. And where you're supposed to keep in mind where I got this from is Pascal's triangle. Keep in mind over here, if I wanted to expand something out, We know anything to the 0 power is 1. So I can say, well, a plus b to the 0 is 1. If I said, well, a plus b to the first, well, their coefficients are going to be 1 and 1. This is the beginning of Pascal's triangle. All Pascal said is that for every other layer of the triangle, each level starts with a 1 and ends with a 1. Any other number is the sum of the two above it. So 1 plus 1 is 2. This would give you the coefficients of a plus b squared. You'd say, oh, it's 1a to the second plus 2ab plus 1b to the second. If I have a plus b cubed, the coefficients are everything starts with 1, ends with a 1, and then the other two, 1 plus 2 is 3, 2 plus 1 is 3. Now, the way you always read each of these levels is the first term is the coefficient of the full power of the first term. So I'll say the coefficient 1 goes in front of the full power on A. If you had to put a b there, it would be b to the 0. The next term, it's the coefficient of a to the 1 less power, second, and then as you decrease the power on A, you increase the power on B, so 3ab to the second. The next term, decrease the power on A again, so 3a to the first, b to the second. And then my last term, 1b to the third. A decreased all the way down to the 0 power, so there was no point to even write it in there. Now, when I come over here and say, what in the world does that have to do with this problem? It has to do with it because of this. I'm supposed to apply the formula f of a plus h minus f of a over h. So, in applying that formula, it's all just going into the cubed function. So I'd say, well, my first term, now I did a plus b over here. My formula says f of a plus h, so it's going to be a plus h cubed minus a cubed, all divided by h. Now, you would either have to multiply out a plus h times a plus h times a plus h to get this 4-term polynomial here, or use Pascal's triangle like I've showed you here. I think it's a shortcut. Please don't be one of those students that says a plus h quantity cubed is a cubed plus h cubed. That drives me nuts. So I'll say, okay, a plus h to the third power, as I've shown over here, it's just going to be 1 times the full power on a. So 1a to the third, I'll just call it a to the third. Then the next term has a coefficient of 3, a to the second h, plus 3, a to the first, h to the second, and plus 1, h cubed. All of that is my a plus h quantity cubed. I'm subtracting from that a cubed, and I'm dividing it all by h. So as we can see, the only thing that's going to cancel is the a cubed. So you'll be left with every term in the numerator that's remaining will have that common factor of h. If I factor that h out, I'll have 3a to the second plus 3ah plus h squared. All of that over h. At this point, I can eliminate h, since there's an h factor in the denominator and numerator, and you have your final difference quotient solution, 3a to the second plus 3ah plus h squared. The instant you can cancel h out of the denominator as a factor, you're done. Now, those are really by far the most important problems in this section. If I looked at one more, there were several problems in here, 55 through 72, that had us look at finding the domain of a function. So let's say, for example, I look at one, an even problem like number 70. I'll call this number 5, and it simply asks me to find domain. And the problem it gave me was f of x is equal to x squared over the square root of 6 minus x. Now, this is actually a very quick and very easy problem. So when you think about it, it's a rational function. You have a polynomial in the numerator. Well, actually, you have a square root in the denominator, so not quite a rational function. Rational functions when you have a polynomial divided by a polynomial. But when I'm thinking about the domain, the numerator is not going to have any restriction to the domain whatsoever. You know, x squared can exist for all values of x. You can't mess up the numerator of a the numerator of a fraction, no matter what term it's equal to. So that has no effect to the domain of the function. But now when I'm looking at the denominator, one, I know since it's in the denominator, it cannot equal 0, because anything divided by 0 is undefined. Also, though, since it's inside of a square root, you know, you can't take the square root of a negative number or else you get an imaginary solution. So what I need to say for the domain of f of x, the term that's in this square root. Now, because it's in a square root, we would say it needs to be greater than or equal to 0. Since it's a square root in the denominator, it can't even equal 0. So your domain needs to be 6 minus x is strictly greater than 0. And then the easiest way to solve this is just to add x to both sides. And you can say, well, 6 would need to be greater than x. Now, if you did the 3 types of solutions like we've shown in class, you could say, well, I could solve for this on a number line. You just say, well, this means reading it backwards, x needs to be less than 6. So the only value of importance on a number line would be 6. X cannot equal 6. But it can be anything to the left of it. The set notation, it would just be, this is the set of all x values such that, and you could write it just like this right here, 6 is less than x. Most people would write that as x is less than 6. It does not matter. What's up here is the same as what's here. But the way I would want it regardless is interval notation. So interval notation answer, and this is what I'll ask you on the test, is that x is equal to the interval of all x values between. It can start at all the way at negative infinity, and it can go up to 6 but not include 6, so we close it off with a parenthesis instead of a bracket. If it could equal 6, you would close it with a bracket. Okay, that's it for section 2.1.